Chapter 4 deals with measures of variability. Variability is defined as the degree to which a variable's values are dispersed around a measure of central tendency. When scores are quite closely clustered together, variability is low. Where scores are very spread out, variability is high. Examine the scores in these two distributions. The mean of both distributions is 8. Scores in the second distribution are much more spread out than are those in the first. Therefore, the second distribution has greater variability. Let's talk a little bit about variability for categorical variables. Pragmatically speaking, there are no very, very widely used, well-known measures of variability for categorical variables. In this course, we're simply going to say that for categorical variables, when cases are spread out fairly equally, which is to say when there are fairly equal percentages of cases in the different categories, variability is high. On the other hand, in some situations, most cases, very, very high percentage of cases might be in a single category, and very low percentages in other categories or in the other category. And in this situation, variability is low. As you look at variability, you can look at both numbers of cases and you can look at percentages of cases. And it's going to be most helpful to focus on percentage of cases. Percentage of cases gets most clearly at the concept of variability. Let's look at the three distributions in this table. In distribution 1, all cases, which is to say all eye colors, are in a single category. 100% of persons in distribution 1 have blue eyes. In distribution 1, eye color has no variability at all. In distribution 1, eye color is a constant, something that does not vary. And eye color, indeed, in distribution 1 is not a variable. Let's look at distribution 2. Here, almost all cases have blue eyes. And again, I recommend focusing on percentages. So in distribution 2, we have a situation where variability is quite low. That's because, the cases are almost entirely clustered in a single category. Now, on the other hand, look at the percentages in distribution 3. The percentages are very nearly equally distributed in the different eye color categories. 38% versus 32% versus 30%. So this is a situation where percentages in the different categories are very nearly equal, and so this is a situation where we would say there is high variability. Now, if all cases had the very same percentages, variability would be higher still. But I do think that these three distributions give you a good sense of how to assess degree of variability for categorical variables. So distribution 1, no variability at all. Distribution 2, very limited variability. And distribution 3, high variability. We're going to shift now to the measure of variability for interval ratio level variables, which is to say measures of variability for numeric variables. And we're going to look at 4 measures of variability used with numeric variables. range, interquartile range, standard deviation, and variance. The range. The range is defined as the highest value minus the lowest value. And here's a formula. Let's consider the values presented here, which are ordered already from low to high. The highest value is 9. The lowest is 3. To compute the range, we subtract the lowest from the highest. The range here computes to 6. The range is easily understood. It's commonly used. It's a useful measure of variability. Our second measure of variability is the interquartile range, which is defined as the score at the 75th percentile minus the score at the 25th percentile. And here is your formula. As an example, suppose that the score at the 75th percentile is 50 and that at the 25th percentile is 30. Then the interquartile range computes to 50 minus 30, or 20. The interquartile range, sometimes known as the mid-range, sees occasional use in human services research, perhaps a tad more than this, but it's not a highly frequently used measure of variability. We're going to look next at the mean deviation, and I didn't actually list this as one of the measures of variability for numeric variables because it's not used much in research. So we're really using the mean deviation as a tool to learn about the standard deviation, which is going to come next. So here is the formula for the mean deviation. Let's go over symbols again. Recall that the sigma is our summation sign. X conveys an individual value. X bar conveys the mean. N is the sample size. The two vertical bars stand for absolute value. As for instance, the absolute value of -5 is 5. So this formula is directing us to find the mean, and then for each case to subtract the mean from the case's value to determine the case's deviation score from the mean. Next, the vertical bars direct us to find the absolute value of each case's deviation score from the mean. The summation sign directs us to sum these absolute values, and finally we divide by n. The mean deviation is intuitive. It's easy to understand. It's straightforward. It's almost never used. We're using it here to introduce the standard deviation. Let's go ahead and calculate the mean deviation for the 5 scores that you see here. 1, 4, 5, 6, and 9. Observe that n equals 5. Step 1. The mean computes to 5. Step 2 calls for calculation of deviation scores from the mean. So for instance, what is the deviation score for the value 1? To compute the deviation score, we subtract from the score the mean, and that yields the deviation score. So the deviation score for the value 1 is -4. Let's do one other one as a for instance. What is the deviation score for the value 6? To calculate, we subtract the mean, and that yields 1. So the deviation score for 6 is 1. The third step, conveyed by the vertical bars, is the calculation of absolute values. So what happens here is that the negative values convert, so to speak, to positive ones. So step 3 computes our absolute values. Step 4 sums the absolute values. This is what the summation sign is directing you to do. These sum to 10, and finally we divide the sum from step 4 by sample size to yield the mean deviation. So our mean deviation in this example computes to 2. The standard deviation is by far the most widely used measure of variability for numeric variables. Here's our formula. The steps of the formula are: find the mean. The second step, just as was so for the formula for the mean deviation, for each case, subtract the mean from the case's score to determine the deviation score of each case from the mean. The next step, symbolized by the squaring symbol here, is to square the deviation scores. Next, we sum the squared deviation scores. The sigma symbol directs us to do so. The next step is to divide the sum of the squared deviation scores by n-1, and the final step is to calculate a square root. Here's our calculation example. We've got 4 values, 1, 4, 6, and 9. Let's go through the steps. First, we calculate the mean, which is 5. Next, we calculate the deviation scores, shown here. The third step squares the deviation scores. The fourth step sums these scores. They sum to 34. The fifth step is to divide by n-1. So n equals 4, so we're dividing 34 by 3. We get 11.33. And finally, we compute our standard deviation by taking the square root. Our standard deviation in this example computes to 3.37. The standard deviation is truly the workhorse measure of variability. Having said that, it's a little bit difficult to interpret just straightforwardly what the standard deviation conveys. The mean deviation is more straightforward. The mean deviation is basically the average difference from the mean. But the standard deviation is a bit more complex. You take square root. First you square and then you take square roots. So it's just a little bit tricky to interpret it in the most straightforward way. Now, I think that a pragmatic thing that you can do as you think about the standard deviation is think about it as typically computing to a value that is just a little bit larger than the value of the mean deviation. For instance, in our just finished calculation example for the standard deviation computes to 3.37, and the mean deviation computes to 2.5. So the standard deviation is just a little bit larger in this situation. So as I just mentioned, the mean deviation conveys the average amount by which values differ from the mean. So the standard deviation is communicating to you a value that is just a little bit larger than the average amount by which values differ from the mean. But study the formula for the standard deviation. Think about the standard deviation. We're going to use it a lot in both descriptive statistics and in inferential statistics. I symbolize in this text the standard deviation by small s, capital SD is a frequent way for symbolizing the standard deviation. Let's examine some characteristics of the standard deviation. One important characteristic is that neither adding nor subtracting a constant affects the value of the standard deviation. So suppose that a professor measures the heights of students in her class and that she finds the mean height is 5'7" and the standard deviation of heights is 4 inches. Now, suppose that she subtracts an inch from all heights, perhaps to adjust height for how height is changed by wearing of shoes. So she's subtracting the constant 1 from all scores, from all heights. The mean height will decrease by 1 inch. On the other hand, the standard deviation will remain the same. After subtracting an inch from all heights, the mean will be 5'6" and the standard deviation will remain unchanged at 4 inches. Our final measure of variability is the variance, and the variance is a close relative of the standard deviation. The standard deviation is the square root of the variance. The variance is the standard deviation squared. So if the standard deviation equals 5, what is the variance? We square 5, and in this situation the variance is 25. The variance equals 36. What is the standard deviation? In this situation, you'd take a square root, and we would find that the standard deviation equals 6. Computation of the variance is easy enough. To compute the variance, one follows the same steps as for the standard deviation, but simply omits the final step, the taking of the square root. So in our example, variance computes to 11.33, and you can see the symbol for the variance is s squared. The big disadvantage of the variance is that in interpretation of its meaning isn't intuitive and straightforward. In essence, the variance has a mathematical rather than an intuitive meaning. It's used often, particularly as one progresses to more advanced statistical applications. And that concludes Chapter 4 on variability, and it's on to Chapter 5 on shape of distribution.